Okay, thank you. It is my pleasure and my responsibility to give the first talk at this workshop. And well, yeah, I work on high energy physics. I'm a theorist, but in at least half of my time, I worked very much close in connection with our experimental colleagues doing the physics of the LHC, which is the first acronym that I will keep repeating over and over. It means the Large Hadron Collider based at CERN. As an organizer and also as a first speaker, let me tell you that preparing these talks is not easy, and success is not guaranteed because there is a large fraction of the audience for which, well, even the standard model, okay, is a buzzword, right? While for us, the standard model, in spite, for us, high energy physicists, in spite of the not very appealing name, okay, is the core business. It's the important thing. It's the standard model of fundamental particles and interactions, and it corresponds to the present day understanding that we have of fundamental interaction physics, and that it's really our mission to has been our mission for decades to establish this model, is being our mission for other decades to check and test this model and confirm it, for example, by discovering the Higgs boson, and will be our mission for decades to keep checking this model with the hope, okay, of finding that this model is not adequate, to find something that we like to call new physics, which means new physical laws, maybe new physical particles, or maybe not, and their new interactions that should be included in addition or in substitution of this fundamental model that is the standard model. So I guess that the first thing to understand when you want to understand something from high energy physics talk is that the model is the most important thing. Okay, that the very end, what we want to do is not a tool. It's really what we are looking for. We are really looking for establishing this theoretical construction as the one that describes, hopefully or not, even more hopefully, what we see, all what we see, okay, in the physics of particles, and in particular in the physics of the LHC. So the title of this talk, How Good is the Standard Model, refers to the fact that for the sake of this presentation in particular, I think I tried to phrase the problem, okay, which is the problem of, I repeat, assessing whether or not the standard model, which you now know what it is the correct description of the data, and in particular of the collider data of the LHC. I will try to speak of this problem as a goodness of fit problem. Okay, so I will formulate the problem in a statistical language, which probably is very much accessible to all of you. And so I will tell you exactly what I mean by goodness of fit, and then, well, slowly, hopefully not too much slowly, I will go to describe how we are addressing this issue in particular. Okay, okay. So again, the purpose, the most important goal is that you understand the scope of what we are doing, and second, that you also understand how specifically we are doing that, and we can discuss. There are other approaches, other things that I will not be able to cover, but the purpose here, I think, is not so much to be complete, while to be understandable. And if the pointer moves on, which it doesn't, okay, which doesn't in any way. Okay. Okay. Okay, so goodness of fit, a light introduction to goodness of fit. So the main concern, I think, that we all have as scientists in general is whether we are or not doing everything right in our calculation or in our experiment. And we are sadly intrinsically unable to answer this question, right? And so we are obliged to turn to an easier question, which is what could be wrong? That is to say, we spell out a number of possible failures in what we are doing, and we check for that specific failure. And these things that we call cross-checks, well, are not at all addressing, if you want, the original question, which was whether we were or not doing everything right. It's providing a partial answer, but we think that once we have exhausted the long enough list of possible checks that we have done, and that we have that our calculation or our measurement survives all these checks, then we can be reasonably confident that we are doing everything right. And these cross-checks are way more easy the more specifically they are characterized. Okay, for example, if I am a theorist working in energy physics, I have all these simulation tools. These are Monte Carlo codes, the famous code called Pythia, and this has a lot of flags or buttons that you have to turn on or off, for example, to include the effect of electromagnetic radiation. Okay, you may have forgotten to do so, and so your simulated data, which corresponds to the theoretical predictions, are wrong. And if I'm sure that that could be something that I've forgotten, I can easily go and check in the log if this thing was turned on or off. If I'm an experimentalist, very similarly, I may want to make sure before I look at my data that have been collected with a detector on which the power plug was connected to the electricity. Okay, and that is also very easy. If it's connected, then I'm doing things right. Of course, the check is easy, but it's partial. Okay, because I'm checking a very specific. If it is, the more easy it is, but also the less powerful it is, introducing a notion that comes from hypothesis test. The possibility, the opportunity that I have to answer the original question are less and less, the more specifically I am identifying the possible failure. Okay, so the power with respect to addressing the original big question, which was whether I'm robust with respect of everything could have been wrong, is getting harder, is getting less and less likely, because if the failure comes from somewhere else, I will not know. In this list, you can go through towards more complete checks, which are also harder. And well, for the case of high energy physics, for example, the detector system is actually an extremely complicated object. It consists of thousands and thousands of little subdetectors, each of which can have the plug disconnected or any other type of failures. So this is also a question which is possible to address, and is getting, and it's already a hard question, okay, whether the detector system I'm using is working normally. And at the very bottom of this list, there is the mission of high energy physics. The mission of high energy physics is maybe I'm wrong, maybe I'm doing things wrong because I believe that the fundamental interactions are described by this standard model SM theory that defines my state of the art. Okay, so I'm selling this as the theory of everything, or almost everything, let's say, not everything, but well, maybe it is wrong. Okay, so is this theory correct? Or it fails? It fails to do what? It fails to account for data. And the data, promising data where to look for these failures are, for example, the one collected by the LAC. Okay, so this is the hardest possible question, which is the core business of our field. And of course, to answer this question, I also have to make sure that the other checkboxes are okay, right? The detector system must be working normally. I must have not made any mistake when I start from this standard model, microscopic fundamental laws, and I make predictions of the data. So everything must go right. But the very bottom of the list, that's what I would like to do. If everything else is right, then I look at my data. I should be able to tell if the data agree or not with the standard model prediction that I made, and with the measurement, of course, that I will comparing with. Okay, is that clear? It is. Now, even more clear should be the statistician version of this question, which is goodness of fit. I think it's called goodness of fit because the question often emerges after you have optimized the distribution parameters. Like a Gaussian, you have a mean and the variance, and you can fit to that, and you find the best fit of all possible Gaussians describing your data. But in fact, the problem is more general. You may even think that the Gaussian is given because the parameters, as it is the case in most of LHC physics, the parameters of the standard model, the free parameters, have been measured somewhere else. Okay, so you can even think to the Gaussian being fixed and ask how well it in fact fits the data. Okay, which means the following: if you do a fit, you optimize the mean and the variance, you will find a minimum no matter what, even if your data have nothing to do with the Gaussian. Okay, even if you have a flat distribution, even if you have some data that go around in a random way, that do not really look like a bump, but still, technically the algorithm will give you a best fit. And so the actual question that you would like to answer to is, given a set D of data, Okay, and B are a statistical hypothesis for their distribution, for instance, a Gaussian. Thus, R provide the right description of D. Okay. And the answer, again, is much more easy the more restrictive assumptions I make on how the true distribution could look like if it is not R. So the more specifically I check, the more effective I am. So, for example, in this case of the fit to a Gaussian, I may say, look, but let's try to fit with the uniform distribution or with the exponential distribution. Okay, so if the quality of fit is better for the exponential distribution than it is with my best fit Gaussian, then there is something deeply wrong. Okay, then my model is clearly wrong. But of course, this is very easy to do, but it's also very partial. Okay, because I can spot out very easily that the data do not look like a Gaussian if they look like this, but if they look like a Gaussian, but there's some little skewness on the right, or if they look like a Gaussian, the histogram of this data with a little bump on the right, I will not know, because if I just fit with an exponential, unlikely I will get a best fit than the one that comes from the Gaussian. Okay, my data will look normal because the alternative that I have hypothesized, okay, was not complying with the reality, was not able to accommodate the reality. Okay, so it is exactly the same logic that I was outlining before. It's much easier to check very well specified things. It's very effective to check if the failure is that one, but another type of failure, another type of deformation of this Gaussian, that has nothing to do with an exponential distribution, will not be spot out by this simple test. Okay. Well, all statisticians know that goodness of fit is a ill-posed problem, which means that no optimal solution exists. That is to say that there is no operation you can do on your data which guarantees power, that guarantees a certain probability of a certain non-vanishing probability of spotting out the mistake with respect to all possible alternatives. But on the other hand, we know that plenty of good solutions to the problem exist. I would say only in one-dimensional data, but there are also techniques to do more than one dimension. But for example, in one dimension, any student quickly learns that they take a marginal of their data, so they look at their data in one variable only, and they build an histogram. Okay, they build an histogram and they compare with what they expect or what we tell them to expect of this histogram, right? For example, in the case of the Gaussian, they look if the events look a little bit localized around somewhere and they are sort of symmetric if you histogram them, right? And why they do so? Because this often, by experience, allows them to find mistakes. Okay, and so, for example, bin and histogram are a very good solution to this ill-posed problem, and so nothing forbids us from searching from better solutions that, of course, should work in more than one dimension, because, well, one-dimensional data are really not at all normal in energy physics, the much higher dimension than this. But perhaps even in one dimension, these solutions can be more effective. And this is just an invitation to listen to what follows. This is the black represents the probability of finding evidence of some R, okay, R hypothesis, okay, that would correspond, if you want, to the standard model, being wrong at some level of confidence, Z score like 2 sigma, 3 sigma, in the case in which the underlying distribution is chosen to be H1, not R. It's different from R in some specific way that you will know exactly what is later, but it's not particularly important. And this probability, you see, is higher with the black curve, which is our proposal, if you want, but our machine learning goodness of fit strategy, than it is with bin and histogram tests, that the ones that the students would normally do, depending, which, by the way, was sensitivity depends on the number of bins that you decide to do when you construct, right, the bin and histogram. And this is another type of new physics, or let's say another type of possible non-R behavior, which we can also spot out, but also chi-square can do, depending on the binning you choose, it can be more or less effective. And this is, for instance, a Kolmogorov-Smirnov for other one-dimensional tests that you can do. Okay. So in the context of the Large Hadron Collider, what is that we want to do? I repeat, we would like to find some evidence or some suggestion that this standard model theory fails, okay? Fails to describe the data, suggesting the need of BSM, which means beyond the standard model, new or different physical laws than the one that we incorporate in this standard model theory. I want to emphasize that this is a tremendously hard task. You should not think to one-dimensional example of this Gaussian, not at all, for several reasons. The first reason is that the number of observables that we can measure, that experimentalists can measure at the LHC, is infinitely infinite. Because when the proton collides, then you end up with some final state particles, and there are several types of final state particles, dozens, okay? And you can have 2 of these particles or 3, 2 of these particles of different types, and so you have a number of reaction which is very large, and these particles fly in the detector with random momenta, following quantum mechanical distribution, and these momenta you can measure them, okay? And so you can look at the distribution of this momenta, and you can select regions by, as we say, cutting on this momenta. And so if you put all together, you have infinitely many infinite final numbers that you can collect out of the detector, infinitely many observables that you can measure. And the expectation, okay, that we have based on theoretical consideration from experience on several things, that this new physics, this BSM, if it is there, it is in any case going to be a tiny departure from the standard model. Tiny can mean 2 different things. Maybe like you have a distribution which is, in the case of a Gaussian, right? Almost a Gaussian, but with some skewness, a little bit, no, fatter tail on the right. Or it could be like a Gaussian, but then there is a very a very small in terms of number of event peak on the right. So, for example, you can have a large relative correction to the standard model, but only in a tiny probability region. So it's really like looking at something rare in some sense, or a small departure in terms of distribution over a set of things which is a priori very large in many variables. And I will have some illustrative just for you to understand the example of how very simplified version of how these small departures could look like in some concrete example, just for you to have a feeling. And so again, given our big task up here, we are unable to address it. Okay, and so we go for the much easier task of searching one by one certain specific alternative models. Okay, there is the standard model, which has its own physical laws. And then there are BSM hypothetical theories that have slightly different laws that as a theorist I can invent or I can formulate based on some principle, some idea, some convenience. And this BSM model, as much as the SM can do, can be used to make predictions. It will predict some distributions of the data which are different from the standard model, and they're different in a very specific manner. They show their difference most effectively and more prominently in certain observables that we select, and also in certain regions, but let's say in certain observables that we select over these infinitely many. And this process of searching for BSM models, this process of selecting the observables and optimizing then the statistical sensitivity of our analysis based on a specific BSM model is what we regularly call a search for new physics. Okay, so you see, even in the name, we would like to see that the standard model can be falsified. We will look for failure of the standard model theory, but we do so by trying to not confirm, but by trying to discover, to search for a specific alternative to the standard model. And this is because it's much more easy to look for well-defined specific things rather than looking in general. Of course, when we do so, the selected observable, by definition, is not sensitive to another model of physics beyond the standard model, because that one will have its own observable. And so, in principle, this one search will not be sensitive to another possible model, which maybe it's equally interesting, but is not covered. We call this strategy a model-dependent search, for obvious reason, okay? And then, for obvious reason, we are interested in designing what we call searches that are instead model independent. And this is particularly relevant if you think that theorists are not enough smart to having formulated, okay, postulated the possible new physics model that is really the one that can be found and is present in the data. If we have failed, then most likely we will fail to see that the standard model fails, okay, because we are searching in the wrong place. And so the importance of looking at the data in a less biased from theory manner stems from this concern that more or less we all have. And the model independent searches then should really go straight towards the goodness of fit idea. So we have a standard model that I will call reference model, R, okay, capital R, hypothesis, that I want to compare with the data without reference to an alternative physics model. This, just for the expert in the audience, don't forget that this type of model, so a notion of model independence already exists and is well developed in the community precisely for this, but this typically amounts to make hypotheses on the nature of this beyond the standard model theory, which are weaker than usual. Okay, you make big containers of models that hopefully will more or less represent the signature of several other BSM models, but the machine learning way is intrinsically different from that. Okay, there are questions?
I mean, if you search for a billion different models, it will be very likely that one of these other models is probably consistent with your data. Statistical fluctuation.
Statistical fluctuation. So I'm not sure. Like, of course, searching for more and more models raises your chance to hit the right one. The space of possible models is not known. Okay, so whether billions is enough or you will need billions of billions, I cannot tell, right? So the class of theories from which we're fishing on is the one that are based on quantum field theories, are based on principles that we believe are absolutely true and correct, but we don't know what is reality. So I cannot answer your question in terms of likely how likely it is that if I do billion searches, we don't get to billion, but we get to 1,000 searches or more at the LAC. If that number is sufficient to be okay, that there cannot be anything else. The idea is that maybe not, and it's important enough the problem to make sure. If the question is in terms of what we call Lukelser effect, that is to say you try, of course, to search for billion of different models, okay, then this is, of course, taken into account. We do know that if we do 10 to the whatever 6 searches, then one has to give 5 sigma or whatever. This is well known. Okay, please.
Fair to say that just from a combinatorial standpoint, the space of possible models is also a thing.
The space.
Yeah, all of the possible.
Yeah. So yes, I think I cannot quantify the degree of infinity, but more concretely, I cannot quantify to what extent. I cannot quantify to what extent, even in the framework of quantum field theory, I've proven all possible models. I cannot. Maybe in the level of perturbative quantum field theory, one can try to make a ranking, like adding this particle, this other particle, and in terms of combinatoric, that explodes very, very quickly. Okay, so but if I think even more speculatively, saying, okay, but suppose I don't know, suppose the framework is different, then go in a space which is too vast to be for me even to try to answer. Yeah, and I don't know. Yes, and I'm not sure I can. Yeah, I understand like the mathematical quantification of these powers of infinity. Okay, please. Heavy vector triplet. Heavy vector triplet. It's a model that contains spin 1 particles in all possible ways, but well, yeah, it's like the SUSY simplified models. It's or dark matters. It's the same. Okay, so right. If I so let me try to make more clear these ideas of goodness of fit and some of the things that I made before, trying to make them more from a simple viewpoint, classical statistics. So let me speak about goodness of fit from maximum likelihood. So the data, like the ones of the LAC, are features X, which can have a number D of dimension that is in principle arbitrary, because the actual data are even much more dimensional than what I will be, or Gaia will be showing, but say few, 10, 20, features, and then you have a large, typically number of them that you collect in the experiments, and those are independent identical distributed measurements of, for example, the momenta of these particles that arrive and hit the detector, and you measure the momenta. The R, that is always like the standard model hypothesis, gives you a prediction for the distribution. I will be more specific of what I mean by prediction in a second, but let's say this is the reference distribution, so the distribution of X given R, and the distribution is not the probability distribution the way I'm speaking. P is normalized to 1, but little n is normalized to an integral, which is the total number of events, of collisions of this type that experiments collect over a year, over a certain amount of time. This is something that you can also predict. So in order to even start speaking about the problem, statisticians, and if you are Bayesian, I think you understand it very well, because if you think Bayesianly, because so if hypotheses have a probability, you have to find the space of the hypothesis such that to assign to them probability 1, okay? But in any case, you really need to define a space of alternative distributions, which is depending on parameters. So it's what is called the composite hypothesis. The parameters are W. These are the alternative distribution, n of X given W. I have not yet specified what is n of X given W. I will do it in a second. So from the maximum likelihood of the late 30s, so I'm not saying something particularly innovative here, there is a way which we can decide to follow to probe whether the the data are well described by the reference, or essentially, as you will see in a second, if some hypothesis in the alternative fits better. Some hypothesis in alternative meaning some point here in the W space. So, and this is constructing the test statistics. So it's a variable T that you evaluate once you get the data. It's the log of the likelihood ratio. You recognize this, or maybe not. This is the likelihood for independent data. You are familiar, so when the total number of events is also varying within the hypothesis, so this is not normalized to 1, otherwise you will have the probability, the product of the probabilities of each event. So here you have the product of the densities times this factor and the ratio in the W, and the R hypothesis takes the log and maximize over W. Okay, this maximization makes the numerator hypothesis to adapt itself as well as it can to the observed data, which are these xi. Okay, and so this number is going to be big normally when the data do not. Okay, so that when there exists a better description of the data, which comes in, which is present in the W space and does not coincide with the R space. So from this viewpoint, you may say that this regular model-dependent new physics searches, the one that most experimentalists do, at least poetically speaking, are done by taking as alternative distribution a specific prediction that comes from a specific model. Alternative to the standard model, you will have a new physics MP model that you can use to predict the distribution of X if the new physics model is true. And in the most, say, extreme case, this new physics model will have no free parameters at all. So this could be a unique, simple hypothesis prediction for the alternative distributions. And as I was saying, this is what is regularly done at the LHC. Now, this is not only easy, okay, easy to do. You don't have to do the maximum because you don't have a maximum over W, but it's also very effective. You know, from the Neumann-Pearson lemma, that if NP is true, okay, using this variable is the best thing you can do in terms of maximizing your chance to see an anomalously large T, and so maximizing your chance to see something weird, something new. Okay, that is the Neumann-Pearson lemma. That holds, of course, only if you know exactly R and exactly what is NP. Okay, so not only it's easy to look for one specific new physics model, it's also more effective. It's also more powerful, please. So the Pearson say you that the maximum power of fixed sites, where power is the probability to see something above a certain confidence threshold, okay, whatever the threshold is, the maximum power. So yes, the maximum power are fixed sites. That is to say, the maximum probability of seeing something weird, having fixed the probability of seeing something normal, or seeing a weird manifestation of the normal hypothesis. It's a bit like the rejection, or now if you're more used with rock curve type of okay, you cut the rock curve when there is a certain alpha, and then you get the best possible beta. if you are more familiar with the okay. No, it's nothing complicated. It's really textbook things. Okay. Just to keep things as simple as possible. Right. What is then a model-independent strategy? Obviously, it's a case in which I do not at all want to go and search for some new physics model. I rather want to take this alternative distribution to be well, something. Okay, to be something which should not say. In the choice of this alternative distribution, I should not use any guidance that comes from theoretical physics, unfortunately. Okay, and I do it on purpose because the idea is really to check whether my guidance was wrong. So I should just get an alternative in some parameterized form. I can write it, for example, like here. It's convenient to write it as in terms of the reference distribution times the exponential of some f function, such that if you invert f is the log of the ratios between the n of x given w, n of x given r distribution, right? You see? And what we should ask to f being, well, several things, but one immediate thing is that it should be a set of functions parameterized by these w parameters that should be flexible enough. In what sense? If f is a very rigid model, now I'm referring to statistical model or set of functions, like it's a straight line, then in the maximization, okay, if the data do not really follow this straight line, but have like a little structure, the straight line fit will not be better than the reference, okay? So the importance of being flexible has to do with the fact that if you don't know what you want to expect, you would like this function to be ready through maximization, to go in a configuration that resembles the data, whatever the data are, differently from R. And so in the Middle Ages, the most commonly used piecewise flexible function approximant family of functions were the piecewise constant functions, the ones in which you decide a certain bins, okay, and the function is constant in each bin, and the height of each function is your parameter, and well, and if you do so, okay, if you insert f like this in this formula, you recover, by computing this analytically in a very complicated way, you recover what is known as the bin histogram test. That is essentially the thing that you have your data collected in regions of X in a large, say, box of X. Then you cut this box into little bins. You count how many events you see in each bin, and you compare this counting with the prediction that the model that n of X given R will give. These are Poisson distributed independently. You can do this. It's independent Poissons. And here is just recovered in a much complicated fashion. And actually, this method is used not so intensively because bins in higher dimensional does not like work very well because of several reasons. But this is actually something that is at the basis of what are really model independent searches that are currently done by experimental collaborations. That is exactly searching, I mean, having this signal or search regions, okay, and counting like this. Now, realizing this, it came to our mind that that since long we think and we believe that there are much better class of universal functional approximants than bins, okay? And well, and we try to explore the possibility that this f function would be a neural network. But of course, our recommendation, I mean, our idea is simply to make a progress with respect to the bins that, I mean, a priori is not difficult. So I don't think I need to convince you that this is a highly motivated attempt because bins, well, suck, especially in high dimension. And as I was saying, and actually, or Gaia or Marco later in this workshop will describe another paper of us in which we did the same thing, but with some kernel methods that can also be employed. So generically, the idea here is to try to see, I mean, what we can put here of this to this f. But with neural networks, it works pretty well. Please.
I mean, the model, the output depends on some parameters,
Right. The model you refer to the standard model. The observation, the measurements are the measurements. Now, the distribution of the measurements, okay, can be modeled by the standard model, but then you're saying on top of this, inside the standard model, there could be parameters. Absolutely, absolutely, absolutely. Absolutely. So there are two types of parameters. The ones that are the fundamental parameters of the standard model, and this you don't have to worry about because those are measured somewhere else. And then there are what we call, or we interpret in terms of nuisance parameters. That is to say, the modeling of the detector, the uncertainties in the measurements of some auxiliary quantities that we have. So what you're saying is correct. So the reference model does contain parameters, and we can deal with that. And I will briefly go through that afterwards. Okay. So in this description here, the reference model is perfect. Is perfectly known somehow. That prior is it's like everything picked, but this can be done. Okay. So trying maybe to speed up a little bit, even if the time is infinite, but maybe for you it would be better if I. Okay. So this slide I want just to show it. It's a curiosity, but it's interesting to me that. So I want to put together this paper of Neumann Pearson of 39 with neural networks. So what I have, please.
The model of the strategy, the NP means like, for example,
for example, you can have we use Lagrangians to model our fundamental interaction particles, and so you can add the new particles to the standard model Lagrangian or a new interaction. Okay, this is a specific new physics model, which.
So there you're thinking actually the one.
There, this n of x given np means that I do a lot of calculations starting from this model, and I derive the distributions very much like I would derive the one of the standard model n of x given r.
And by in the model,
it's the log ratio. It's the log ratio of the likelihoods in the NP that goes up here over the reference. Okay. In the model independent strategy, there is no NP, right? So there's no NP. There is just the idea that there could be some deformation with respect to R, and that my data could be better accounted for something that is different from n of x given R. And so I just want to parameterize this difference in a completely unphysical way. So there is no correspondence between theory and F, or theory that we know. Yeah. So we are learning something about physics. In any case, if we are lucky and get a discovery at the LHC, we will get attention with respect to the standard model in some final state. And in any case, we will have to go through what we hopefully will be called the process of characterization. Okay, so actually what we are doing gives also help for characterization in the sense that you can have, but you will show, I will see in a second. But yes, of course, the goal is to write down the next standard model theory, right? But to start with that, you need to falsify the old standard model theory, okay? Which suggests you where to look at. And by the way, all these things are not, okay, but let's say these model-independent strategies are also supposed to be effective to spot out a place where you're seeing something weird. Then understanding what it is that will really produce the Nobel Prize will take longer, but we will be all happy to do so. Like what? So if you discover something by EFT or by simplified models, still you will like to check whether it's not by chance. It's really the EFT and not the simplified model that gives you that signatures, right? But in any case, then it would be more easy because you have a starting point which is a resonant peak, and then you can start building your Lagrangian more easily. If you have, yeah. Okay. So the curiosity that I want to outline is, so I want to compute this variable given the data, and I want to solve two problems at once. The first one is that the neural network needs to be trained, and so I have to turn this formula into something that resembles a loss function from which I can run training. And the second thing is that, as I anticipated, we do not really have any analytic access to n of x given R. Okay, we can calculate, but this means the following: we have, let's say, we have Monte Carlo simulations that allow us to produce data sets, okay, which are distributed exactly like the data would be if the standard model was true. Okay, this we are very good in doing. Getting a closed formula is generically impossible. Okay. That is to say, the simulation, like all Monte Carlo simulation, goes through latent variables. So they work in the forward mode. You emit, think to the interaction with the detector. That's the easiest thing. There are other phenomena, natural, right? No, not because, so other type of phenomena work the same way, but interaction with the detector, of course, the electron goes and then it interacts, but statistically, right? So these are latent variables that end up in the final, so this we cannot get. So what we can get are samples of data, artificial data, not necessarily artificial, but I will not go, but say we can have access to what I want to call a reference sample, that is to say instances of these X variables that I collect into this R data set that follow the distribution provided by the reference model, by R, okay? And so what I can do is a very simple thing. I have to replace in some place an integral with a Monte Carlo sum, taking into account that when I do so, I introduce errors. So this, like this is an inequality only in a regime of large sample that is equivalent to saying that n of x given R is known, because it is effectively infinitely sampleable. But if I do so, then I get a nice formula that tells me that the Neumann-Pearson T is -2. Minus is because I want to turn the maximum into a minimum. The minimum of this object, which is clearly a loss function. It's a weird loss function. With y equal to 1, I denote the y label, I denote the data, which are the ones that were present already in the Neumann-Pearson, so the Neumann-Pearson, the maximum likelihood formula here. And in this case, the loss is -f. Otherwise, for the other data, I'm training the data against another set of data, which are the reference data. So it's a very simple supervised training in fact, only that we do it with this weird loss function that we just obtained by calculation, just because we wanted to follow the Neumann-Pearson, the maximum likelihood recipe, yeah, as it is. So at the end, the algorithm is. Please.
XI, they are the data, right?
Yes.
And how again do I evaluate the probability of XI given R when XI comes from the data?
So yeah, and now the math here looks it's like often in math. You see, here I have everything under control. Yeah. So here, this formula, the only place where where it enters the reference model, this little n of R, it has to do with the way I've written the things. If I had written the things in terms of probabilities and then the norm outside, maybe it would have been more clear if you don't come from like a standard likelihood. But in this way of writing, the only place where the reference model enters here, which is the total number of expected events, okay, which is the EC integral, okay. It's this thing of math that you say, but how can this be relevant? Well, it would be more clear if I had done it in a different way, but it's indeed relevant. So here, then, since I can only sample, what I can do is a Monte Carlo integral instead of, you see?
That's why you need it very large.
Yeah, so very large or large. In concrete, it needs not to be very large because somehow you have, so, yeah, in concrete, you see, the figure of merit is this. Let's say the total number of expected events in the reference hypothesis should be small compared with the one that you can inject artificially, or but a factor of 5 is fun, in fact, to work. So then it becomes more a technological thing. By the way, another interesting thing is that if we could make smarter this, because this is like doing a Monte Carlo sum in like in totally non-optimized way, right? It's you take the data, you take the sample and you sum with the prior, which is just the one that is coming from an x given R. But the target function now, of course, the target function is varying during training. But if you could optimize somehow the prior by which you generate the reference data, maybe you will. Okay, but I'm going outside the question. Good. So yeah, this is the stupid reason why at the end you need the reference sample, but it's obvious that you need the reference sample because the only thing is that it's the only thing that is telling you normality, that is telling you what the data should look like. Okay, so it's very simple. You run 1 year of the LHC. You can compute how many events. So you can do the expectation of the number of events that are will be collected. Okay, so it's expected number of events in a hypothesis or in the other hypothesis, in which case it's this integral. Exactly. You have, I don't know, W plus W minus is one particular process. You can compute the total cross-section for this. Total cross-section of this gives you the total number of events in 1 year of running or whatever. Given? Yeah. And this instead, in principle, is fixed. In principle, it's one number that I can compute for one process. Okay. So I understand that the extended likelihood beyond LHC physics, I think, is never used. So it makes confusion with these total numbers, but this really is nothing difficult. Okay, this comment maybe is more for the experts. Like again, I just repeat that we have supervised training with the weird loss, but very simple supervised training from class 0, reference sample class 1 are the data, and here we can elaborate more, but this is, I think, more for the experts, and so maybe privately we can elaborate more of where do I really get this reference sample from, if Monte Carlo is enough, if they have to be data driven, but just in regular analysis of LHC, we have something that is called the background sample. That precisely means a sample of artificial synthetic data that maybe come from other data that represent the normal outcome of the experiment. So there is nothing exotic. Here it's the algorithm. The way it works is that each time I collect the data, very much like I would like to do when when I collect the data, very much like for computing T, right? I have to be given with the data, and then once I'm given with the data, instead of doing the maximum, I do the maximum by running the training. So training is run for each on the true data versus the R. Okay. Now, what I get again is this test statistics that should indicate, if it's large, that there is something weird. That should indicate that there is that f of x given w hat, the optimized f of x given w hat, is fitting the data better than the reference is doing, suggesting that there is new physics. And here is a partial answer to what you were saying before. You were asking before. There is an opportunity for characterization by the fact that this trained network, if you plot it or if you cut on it, if you study its dependence over the x space, you will find that it's different from 0. Okay, because it's approximating the log ratio between the true and the reference distribution. We find it's different from 0 in places where there is either an excess, like here, or there is a dip. And so you would, for instance, in this very simple illustrative case, you will discover that the tension, the large value of t, maybe is due to an condensation of event around 0.8. Okay, so there is a way to start the characterization process. Now, all the rest as just that, well, my God. So now, what you have to do in order to, just to make some performance plots, okay? To make some performance plot, what we do is that we follow the classical hypothesis testing. That is to say, we say that large T means that R, is in trouble. And to quantify what large T means, we have to compute the empirical distribution of T, assuming that reality is given by the reference model. And so you compute the distribution of T given R, and we do so empirically. That means we suppose that we are able to generate what we call toy data sets. that is to say, other synthetic instances of the data that in this case are like Poisson, their total number is Poisson distributed according to n of r. So they are representative of what we would expect to see in the real experiment. And we train on them, and we compute t, and we compute this distribution. And then we can, for example, use the notion of p-value to quantify how much big this t is, okay? So how much given t that has been observed, how much is the probability that if r was true, we will nevertheless get this large value of t, and translate it into a z-score to see what is normal and what is not. This is a simple illustration that which you can read two things. This is the empirical distribution of t in the case of reference. So I just throw toys according to R and I train, as I explained, and I get this curve here. You can notice the agreement of this histogram with an asymptotic formula, that is the distribution of the chi-square with 13 degrees of freedom. Okay. Why 13? Well, 13 in this very simple example that we are working on is one that I'm showing here in this plot, is one-dimensional data. So it's a very simple network that I'm using here. It has only 4 neurons. Okay, of course, this is an extremely simple example, but in general, the network we need to use are not particularly big because they are supposed to parameterize the ratio, the log ratio of distributions, and the expectation is that the true underlying new physics distribution is similar to n of x given r. So you don't have to expect this network to have make a very complicated, big and complex job. Okay, so small networks are typically enough, but of course not as small as this. But in any case, this asymptotic formula complies with the theorem that is due to Wilkes and Wald from the 50s, that says that the test statistics should be distributed according to a chi-square with a number of degrees of freedom, which is equal to the number of parameters that are being fit. Okay, so the number of parameters in our network is 13, and then by some surprise, because the theorem cannot be applied straightforwardly, okay, for several reasons that we can discuss maybe later, but with some surprising it works like this. And then in blue, you see the other thing that I'm doing. Now I'm postulating, suppose now the data actually contains some new physics. Okay, I want to test, and so I want to see if I specify some new physics called MP1, I repeat the same operation. My toy data sets are now distributed differently than before, so T is typically larger, and this is what you get in blue, showing that, well, often we have values of T that will be considered large from the viewpoint of the reference, if the reference was true. Okay, so this is quantification of performances. So this is an exponential falling distribution in red, which will correspond to the reference model, and it's more or less what the standard model could do in one dimension. So it's, and the number of expected events is 2000 of this, and the new physics is an additional peak. So there is an additive contribution to the distribution, which is a peak around 0.8, and the area under the peak of the distribution is 10 events over 2000. Okay. This is already generous with respect to what to expect. That is to say, we expect a peak in regions of the probability of the reference, which is small. So here in this case, we have a big effect, but only if we look clearly close enough in this tail of the distribution, because in the total, say, region of interest, the vast majority of the data, if you want, are just coming from the reference. And this is what we expect to be the case at AC. So you don't have to expect, again, the example of the Gaussian with respect to the exponential, like I was doing before. It's really much more subtle than this. So this is a comparison of sensitivity z-score. Sorry, this is the z-score that comes from our strategy, a scatter plot. And on the x-axis, now I don't want to spend too much time on this, but on the x-axis, we have what we call the ideal z-score. So we discussed it before at length how to get like the Neumann-Pearson T, no? Now, when you get the Neumann-Pearson T, then you can do the same game and find the sensitivity that the Neumann-Pearson test has. And this is the optimal test for physics model MP1. That is to say, in this axis, I'm not at all model independent, I'm completely model dependent. I'm declaring that I know what is the underlying new physics, because I do. in the experiment, and I compute a z-score, which is higher than the one that I get modeled independently, as it must be, because the Neumann-Pearson lemma tells me that this is the optimal test for MP1, and I do so just to make to notice that there is some correlation between how much there is to be seen, quantified in a modeling state in a universal way by this z-id and our z. Okay, so this is mostly for illustration, but also to get a feeling of how much sensitivity we lose if we go from a fully optimized test, which is however completely model dependent, to a one that is model independent. And in this case, we lose a couple of sigmas in terms of median. This is another example. So again, clearly the strategy is model independent, which means that it holds, so we run everything in the same way, no matter what is new physics. We don't know what is new physics when we run our thing. So NP2 now is this. So is an excess in the tail of the distribution, pretty small, and in the region which is not much populated either. Okay, and this is another example of how new physics could look like, a small deviation on the distribution. So 2000 versus 90, and you see that the correlation plot remains more or less unchanged, going from one to the other, meaning that even if the nature of new physics from here and there is slightly different, in this case at least, the significance compared with what will be the best possible significance, the correlation, you see, remains very much the same. And this is another example, a new physics which is more abundant, but it's in the bulk, so where the distribution is, where the standard model is large, and this we can see just because there is a lot of event, and so this little green thing is visible, and again, the correlation plot remains remains the same. So this, we say that now, like the performances, or if you want, the performances degradation from the best you can do, and the best you can do if you are model dependent, and the best you can, and what we do if you are model independent, the correlation is robust with respect to the new physics nature. Okay, so let me try to go fast here, and so you please. Sure. Yeah, I mean, when the p-value goes below 0.5, you start getting a z-score on the other side. Okay, so you see less than nothing. I don't know what to say. Okay. Yeah. So here is to come answering to your question that I will not do in full details, but yeah, the predictions that come from the reference model, and I remember the predictions means these simulated events. Okay, these simulated events do not really, I mean, they contain imperfections. Okay, so they do not correspond to what really the standard model will say, and there are plenty of reasons for these imperfections, going from experiment to theory. There are several formulas, but the formulas that is applied in energy physics to deal with this thing is the one on Nuisance parameters, in which you do the following. So the standard model now is not a point. Okay, the reference hypothesis here it has parameters, and so it is this green box, and the nuisance parameters nu are the parameters that correspond to these unknowns that we were discussing before. And then you have a statistics that is the log of the maximum of the numerator and denominator. So the maximum overall parameters in, let's start from the denominator, it's the maximum in the nu space. So you get the best fit that you possibly have in, so you adjust your parameter to fit your data better than possible, compatibly with previous knowledge or independent knowledge on these parameters that come from this likelihood that, for example, tells you that you have measured or you have prior on the response of your detector. Okay, so there is a central value and then there is an error. And in the numerator, you have to put your new physics hypothesis that will be, like in the non-nuisance case, will be the usual exponential of the neural network times the n of x given r, which now depends on nu. So now the numerator depends both on w and of nu. And so this is the good test statistics, for a reason that in our community is considered to be the good thing to do, for a reason that will become clear in a second. And one can turn the evaluation of this ratio of maximi into into a training with a slightly more complicated loss function than the one that I had before, but one can do that. And in fact, there is also one place where machine learning plays a role in this evaluation. It has to do with the fact that the most effective way to evaluate in particular this second term, which has to do with the best fit of the nuisance parameters relative to the to the central value. So here there is another machine learning technique that we like in energy physics, has to do with likelihood-free inference, that is to say, strategies by which you can learn, in fact, the dependence on these parameters, which also are not known analytically as before. We can learn the dependence of the likelihood on these parameters by machine learning techniques. So this would require a dedicated seminar, but it works, and it's used in what we do. And here is the loss function modified to deal with this these uncertainties. Yeah. So in the interest of time, let me just tell you what is that. So why in energy physics we do this nuisance parameter, this strategy here that we are following here, is because since the LHC results are supposed to be frequentist, it's impossible to make a frequentist hypothesis test if the distribution of T, okay, depends on the nuisance parameters. Okay, so if your distribution of T, P of T given R nu, was depending on nu, for a frequentist, it would not know what to do. Probably you should take the maximum p-value scanning over all possible nus. It's something that you cannot do concretely. Okay, so the independence of the test statistic distribution on nu, that is to say, on the true value of these nus that in a frequentist setup exist, is essential for proposing an hypothesis test in this context. And this is ensured in this setup. That's why it's so widely used. Again, by the Wulzer theorem, similar to what I was telling before. The asymptotic formula for this case will be that you get a chi-square in the asymptotic limit, which converges to the number of degrees of freedom, chi-square with the number of degrees of freedom, which is the number of parameters in the numerator minus the ones in the denominator, okay, which is the number of parameters of the neural network as before. And so, given that we have this, we can go and propose to use this for addressing issue. Now, if you want to see more concretely why this is useful, you look here. So this is a case in which there is well, it's a more realistic setup. In fact, no, this is still one-dimensional, but then Gaia will show you something more realistic. Here there is in green, the value of this tau. Essentially, tau is what you will get more or less by running the algorithm without taking into account that there are imperfections. Okay. However, the data that we are using for this, for this coverage test, if you want, the data are generated according to some nu which are compatible at 1 sigma with what you have, but they're different from 0. And so the algorithm discovers that there is something weird and makes a large value of T, which will lead to a false positive. If it was not, that then by this second term that we call delta, you recover the distribution of the chi-square according to the, following the result that you expected. And so in all cases, okay, that's always the distribution that you expect independently of nu. So if you want, you recover any false positive when the modeling was, if you want, imperfect. Okay. Okay. So I'm really going too long, because then Gaia is supposed to show some concrete results using this method. The last thing I wanted to mention, maybe Gaia should repeat this because it's not going to be particularly clear. It's clear that it is clear that the essential, a very important aspect of this type of activities is to understand and decide the hyperparameters of the model. Which model are you putting? Which neural network and which regularization parameter? Because you have to regulate this neural network, because an unregularized model will just make an infinitely high peak around any individual point, or at least choose one and make infinite test statistics, make infinite discovery of new physics in all possible places. So clearly there is a notion of smoothness that you have to enforce in some way. And we're not so happy of the way we are doing, even if it works. We are doing this by a weight clipping. And the optimization of this weight clipping, even if it's not that important for performances at the end, but the optimization, for optimization of the weight clipping, we use this asymptotic formula backwards. That is to say, we have a fixed data statistics. In the asymptotic limit of large data statistics, you would recover the asymptotic formula. So in our case, we make the fit model simple enough to agree with the asymptotic formula, okay? So the asymptotic formula, somehow, the compatibility with the chi-square before uncertainties are introduced, it's used as a criterion for model selection, which essentially is like saying that if you violate the asymptotic formula, it means that you're sensitive to low statistic portion of the data set, which is what we also call overfitting in different contexts. So I don't suppose this to be particularly clear to you, but it's just to tell you that even if it's a simple classification property problem with just with the loss function, it's a bit weird, but this doesn't change much. The task is really different. The task, there are differences between cat and dogs that maybe we can discuss with many of you better. Okay, but now let me go, I think, to the conclusions. Right, Gaia? Did I miss saying something that you will need absolutely? Okay, very good. Okay, so Gaia will convince you that on top of being defined, as I try to show you, this strategy has been applied to problems of the same scale of complexity of a real LAC data analysis. Okay, and there is, I mean, there is a work, I think, in progress in CMS to have a first analysis based on this, and this is absolutely essential because we really want to know if this works with real data and not only on simulation. In particular, we think we understand the systematic uncertainties. We think we understand the mismodeling, but we have to check, right? Because then the data will tell us whether we did. There are a number of challenges of implementation that, depending on now this is not going to be applied, of course, to the all LAC data, right? We will consider a subset of them, producing 2 objects, like 2 leptons or 4 leptons of increasing complication. And there is a number of things that could be improved to make this thing work better, and many of which have to do with machine learning, like, for example, the generation of toys, or the better or faster Monte Carlo simulations, that are all things that you will hear about at the talks during this conference. Generative models for enhancing detector simulations, or also for getting faster or better calculations like of the reference Monte Carlo. There is the connection with something that will come again out probably next week about studying EFT. That is to say, that you will see it's connected with something that has to do with dealing with nuisance parameters in this particular context, and also either Gaia or Marco will tell you more of a non-neural network method called Falcon that we use in place of neural network, which has a clear advantage in terms of training, which is essentially 0 time and not so inferior performances, that you will hear more about in this general talk by Marco about this kernel methods that he's working on for other also for other reasons. Okay, so the problem, as I was saying, is general. So it can be phrased as a goodness of fit problem. So, for example, if you want to do data validation, to check that the data that come from your detector are the same ones that are coming that were coming last week. Okay, this is a gigantic problem in energy physics, and a little thing of this we are doing. Okay, it's the same goodness of fit problem as it is. Also, if you want to make sure you haven't made theoretical mistakes, you want to compare different predictions or Monte Carlo generators, you can try to use these things. Of course, applying any of these techniques will not guarantee that if we find something weird, okay, some tension with respect to what you expect, it's really due to new physics. Okay, this is impossible to do. So the most, let's say, the a possible explanation would be that we haven't understood our background, we haven't understood our simulation, we haven't understood our calculation. And that's our job, right? To find whether we have understood our simulation or calculation or not. So I suspect that for sure we will find plenty of places. If it's true, as it seems, that this method is more powerful than just looking at histograms by eye, we should find plenty of wrong background estimates when you wrong modeling that come from mistakes in calculation, but maybe also new physics. Thank you. Yes, maybe in the meantime, Gaia you can come and okay, ask the question. I was just wanted to speed up.
Okay, thank you very much for the talk. So did I understand it correctly? So obviously there's the one thing that the number of parameters of the neural network needs to be controlled. If you have more, then the chi-square has more degrees of freedom, right? So that's one thing. But did I understand you correctly at this one point that this is not enough, because even with very few parameters, you can fit one very high peak on one data point, and that would spoil things, and that's why you have this weight clipping. I see, and that probably then makes the distribution, so the distribution of T then also changes, right? So there must be an influence, so you don't have the simple chi-square curve anymore, right?
Exactly. So the sensitivity to rare features does not depend on the architecture, on the number of parameters. You can have even a very simple neural network. 2 neurons is enough to make an infinitely sharp peak, right? Well, at least in one dimension, then in more dimension. So the need of, so there is a notion of smoothness that you have to enforce on top, and that is independent of the number of neurons or parameters that you have in the network. And so we would like to have a better quantification of this smoothness, a better measure, such that to impose something that looks more cool than the weight clipping, also because the weight clipping unavoidably forbids you to have peaks, which is good, but on the other hand does not allow, forbids you completely. It does not, that penalizes, it really does not allow them. So very narrow signals that we cannot see because of this limitation. So there are a number of things that we are looking at to understand this better. In terms of the selection of the neural network model, the hyperparameters, then what we find experimentally is that if you go larger and larger in the network, at some point, either we don't know, either because training doesn't make it, or because if you want, the complexity of the statistical exploitation is bound. At some point, the chi-square, so this distribution does not keep growing forever. Okay, but this may also be due to the fact that training is low, so we're not sure if it is. But in any case, what we have is at the end something by which we fix both the hyperparameters and the weight clipping. Connetti da Zoom, no? Ma connetti da Zoom.
Yeah, I don't know if I fully understand, but does the same method can be used for different applications? For example, if the reference model is the simulation, like the analytical one, we can see how beyond standard models deviate from that one. Or if the reference model is data from the LHC, you can use it, I don't know, like for anomaly detection or something.
Yeah, that's precisely the point.
Oh, okay.
So the reference is what gives the normality. So if the way you manage to get it, if you manage to get it analytically and then you sample, or if you get it from simulations, then you can compare with the data. Or you can compare two possible models, two possible predictions. Okay, just to check that they are compatible. Or you can check data from data. And this is, for example, when you have you want to spot out an anomaly that, for example, a malfunctioning of a detector will show up like this. You will have one month of data taking under normal condition, and then you will check 1 week of issues, and you will find the issues, and Gaia actually show plots that, in this case, it's a data-to-data comparison.
Okay, thank you.
Okay, so hi everyone. Once again, I'm Gaia. I'm a PhD student with the University of Padova and at CERN. I am an experimental particle physicist. I'm part of the CMS collaboration, but today I'm going to talk about new physics learning machine, which is the way we call the algorithm Andrea already introduced for you just before. So the idea for this talk is to go through the main concepts that Andrea already introduced and providing you with some more technical details or some aspects about the machine learning implementations, and in the process to give you some examples, so an overview of the examples of the possible applications of this algorithm. So yeah, as I said, Andrea already introduced the topic, and yeah, there are a couple of applications. Of course, NPLM has been designed in the first place to solve the problem of model-independent new physics searches in collider experiments like at the LHC. So, of course, this is the first kind of applications, but then, as Andrea already mentioned before, there are a couple of other possible use cases like data quality monitoring or validation of generators. I'm not going much into the details of validating generations. I'm going to talk quickly about DQM, and then you'll see tomorrow from Marco from his presentation for about kernel methods for high energy physics, something more, because one of the applications of kernel methods to high energy physics we've been working on is this new version of NPLM, where we substitute neural networks with kernel methods. I'm not going to spoil more about this. This is going to be the topic of tomorrow presentation, so I will let it to Marco. But I'm going to give you some ideas anyway. So I'll start revising quickly what Andrea already said, adding a little bit more about machine learning. First of all, discussing about the implementation of NPLM without the present systematic uncertainties. And here there are some main concepts about this. So once again, what is the main goal of this algorithm? The goal is to compute a log-likelihood ratio hypothesis tests. The log-likelihood ratio is the standard approach adopted at the LHC experiments to perform hypothesis tests, and it allows us to compare the likelihood of the data under two different hypotheses, a reference hypothesis or a null hypothesis, which is usually our standard model, and an alternative hypothesis that here I call HW, and where W are the free parameters, and I already talked about it. And usually in standard kind of analysis, this alternative hypothesis is already specified a priori. So we have an idea in mind of a specific new physics signal, and we sort of add some information about it in the description of this model. With NPLM, with our algorithm, we don't want to do this. We want to be completely or as much as possible unbiased on or agnostic about the nature of the signal. So the way we do this is we sort of parameterize the distribution of the data under this alternative hypothesis in terms of the distribution of the data under the reference hypothesis, so under the standard model, using a neural network with this parameterization that Andrea already showed you before. And by doing so, we can learn the distribution of the data under the alternative hypothesis directly from the data. And so we keep our model, our algorithm signal model independent. How do we do this? It's just we translate the problem of maximizing the log-likelihood ratio test in the problem of minimizing a loss function with this form. And Andrea showed you before the way we get to this formulation, so I'm not going to go into the details about this. Once again, I want to just remind that here you see there are two sums, one over dataset D and one over dataset R. So we have two training samples. The first one, D, is the dataset we are interested in testing, while the second one, R, is our reference sample. We use it to describe or to depict our reference hypothesis, in general, the standard model. It could be a simulated sample, so it can come from Monte Carlo simulations. It could be data-driven, so it could be, there are many techniques to build it. Those are usually standard techniques and they are used in standard analysis, so there is nothing new about this. The only new part is how we use it. So this is a schematic view of how the algorithm works, again, without thinking about systematics for now. So we have our neural network that takes as input the two data sets, and we label them. So we give label 0 to the data set of reference, and we give label 1 to the data set of interest. And so we train this neural network to minimize this loss function here. And once the training is over, the final configuration of the model, which is this F here, will give an approximation of the log ratio of the distribution of the data under these two hypotheses that we are using for the comparison. And this, as Andrea already said, and as we were discussing before, is already an interesting information because it allows us to characterize a possible discrepancy that might be present in the data. So for instance, if we have something like an exponential distributed reference hypothesis and we have some data where there is a small bump, we will expect something for the log ratio of the distribution, something which is 0 everywhere except for a bump in correspondence of this peak. And this is already something that gives us an insight on which kind of discrepancy might be present in the data with respect to the normal behavior that we expect in the standard model hypothesis. But then, as I said at the beginning, we are interested into a test statistic. So what we need to take out of it is a scalar, a number to use as a metric for a test statistics. And the way we do this is just by taking the final value of the loss function, you see it from here, at the end of the training, multiplied by a -2, it's also here, and this will give us a value for a test statistics. Then, in particle physics, at the LHC experiments, we adopt a frequentistic approach, the way we quantify discrepancies by computing p-values for a discovery. So we need, again, also here to compute a p-value. And the way to do this is by building this distribution for the test statistics under the null hypothesis and compare it with the value of the test statistics observed in the data set of interest. And then the p-value is just the right tail of this distribution. So how do we do this? We take this framework and we run it several times under the null hypothesis. So we substitute the data set of interest with pseudo data set, which are distributed according to the reference sample. So in a way, we want to see what happens if our data set are distributed according to the standard model. So in a way, they behave normally. And we train the neural network. So we train a neural network every time for each of these pseudo data set. Every time we extract a value for the test statistics and we use it to fill this histogram. So in the end, we have an empirical distribution for this distribution of the test statistics under the null hypothesis. And once we've done this, we can run the algorithm just once more on the real data or the data set that we want to test. And this time we get the value t-obs for the test statistics, and then we can compute the p-value out of it. So here I have to make a comment about the actual shape of the distribution. Andrea already talked about the asymptotic chi-square distribution that we target. And I'm going to give you a little bit more details about it just now. So as Andrea said before, well, the idea is about NPLM, about this algorithm, is to try to approximate the log-like ratio test statistics. And due to Wilks and Wald theorem, we know that asymptotically, this test statistics should follow a chi-square distribution with a number of degrees of freedom equal to the difference in size of the parameter space of the two hypotheses, when one of the two hypotheses is containing the other. And if you're doing our job well, if the algorithm is working well, we would expect something similar also for our algorithm. So we would expect the algorithm to provide a distribution for the test statistics under the null hypothesis, which is a chi-square. and the number of degrees of freedom that we associate to this chi-square is the number of trainable parameters of the neural network. Yeah, I mean, it's an upper bound for number of possible degrees of freedom of the model. I'm not going into details about this, but if you have questions, you can ask me later on or whenever. I mean, anyway, if you have any questions, just please stop me and ask. Anyway, what Andrea already showed before is that there are situations, easy problems where this chi-square behavior is seen naturally in the distribution of our test statistics, but then there are situations where we don't observe it empirically by default. But we've seen, again, empirically, that we have a way to regularize our neural networks so that we recover this chi-square distribution anyway. And the way we do this is by adding a regularization technique, which in this case a weight clipping parameter, which is an upper boundary to the value that each trainable parameters in the neural network can take. So it sort of limit the space of the parameters, the space of the possible configuration of the neural network. And this we have seen just the same empirically that that works in a way. I mean, what we've seen is that we can scan the value of that this parameter takes, and we will eventually find for a given neural network a value for this parameter for which the empirical distribution of the test statistics actually match a chi-square. And okay, this is just an example where I have a neural network with two layers with 7 neurons each, and these are expected number of degrees of freedom 106. And then you see here some example of the empirical distribution of the test statistic with different value of the weight clipping. You see that if the weight clipping is too high, the distribution slightly moves to the right side, while if it is too small, it moves to the left side, but then there is an optimal value for which the compatibility is good enough. And this also guarantees us that the training is stable. So in a way that these are the curves of the percentiles of this empirical distribution, then they are directly connected to the value of the loss function, because the test statistics just minus twice the value of the loss function. So when we see these percentiles get into sort of a plateau, we are also guaranteed that the loss function has reached a plateau, and so that the training has sort of reached a stable minimum, which is actually something important when then, since then the purpose of this is to compare with between different trainings of the neural network. So if you're not sure the network does converge on something stable, we cannot really be sure that the p-value we quote is robust. So this is important. And yes. Well, it's the regularization here is kind of different from usual machine learning techniques, because first of all, the size of neural network here, it's true that it's small, but we don't really need such a big neural network for this kind of problem, because as you've seen maybe before in this plot, most of the time, so our neural network should be something equal or similar, very near to zero most of the time, and have just small departures with respect to zero, because we expect the BSM or any source of discrepancy to be small, a small perturbation of the standard model. So in general, we don't need that much flexibility, let's say. So that's the reason why we see that our algorithm works with small neural networks. But it's true that in general, for like more standard techniques based on machine learning, this doesn't happen. And also, we don't have any other form of regularization implemented. So usually when you do some supervised approach. You usually have some validation techniques, like you have a validation training and a validation training split, and so you use this to stop your training and to avoid overfitting. We don't do this in the first place because we want to overfit, so we really want to fit the data, okay? But at the same time, in this way we are subjected to, let's say, overfit point in the data space which are sparse. The reason why this is a problem is because our loss function is unbounded from below, so we need somehow to provide a limit, to a lower limit to it. That's the reason. So back here. So far, I've just shown you how we can implement how we can implement NPLM in absence of systematic uncertainties, and this is already enough to face some kind of applications. For instance, the data quality monitoring, because as Andrea already told you before, in the case of data quality monitoring, we imagine to have a large set of data that we collected in some normal condition of our detector, and then let's say we acquire more data, a smaller set of data, and we want to check whether that new sample is still compatible with our expectation for normality. This is something where we don't need to add systematic uncertainties, because the two samples, they come from the same source, they are both data driven, so we can just compare them. And here, so we can just use NPLM the way it is without systematic uncertainty. So I'm going to show you quickly an example about an application for DQM. Marco is going to talk about this tomorrow better, because it's something we do with this kernel method implementation, but this is just to give you an idea of what can be done. So let's say, so we consider this drift tube chamber that is located in Legnaro, in the INFN National Laboratory in Legnaro. We have this thing here in the photo is a drift tube chamber, and it collects cosmic muons. How does it work? We have, when the muon pass, the gas inside this chamber ionize, and the electron drift towards us the wire, producing a signal. We have 4 layers, so when the muon pass, it produces, let's say, four different signals, and we use these hits to fit a trajectory. So there is a reconstruction algorithm that provides us with a slope for this trajectory, and it also provides the drift time, so the time that takes for the electron to move from the point of where the muon passed to the wires. And those are some variables that we want to monitor while we acquire data. So we have these 4 drift times, 1 per layer, so 1 per chamber, let's say. And then we have the slope, and well, okay, this is an additional variable, which is a number overall hits in the chamber, and we can look at how the distribution is in normal cases. This is this light blue histogram here, and then we can what we've done here is, as an exercise, is just trying to see how this distribution varies when we inject on purpose some anomalous effect in the detector. So like we vary a threshold tension, and this variation makes our distribution change. And here's just an example of what will be the output of our test statistics. And you see in normal condition, it's this narrow distribution here. And then when you apply some effect to some modification to the detector that cause some anomalous events or some anomalous behavior, you will see the distribution to shift to the right side, and progressively with the magnitude of the anomalous source that we injected. But Marco is going to talk about this tomorrow, so I don't want to say more. And yeah, so this was just an example of what we can do in absence of systematic uncertainties. But then, as I said, the main purpose why we designed NPLM is to solve the problem model, sort of trying to give a solution to model independent search for new physics at the LHC. And for this kind of problem, we need to have a way to deal with systematic uncertainties, because in this case, our reference hypothesis, the standard model, is not perfect. We have some, so there are uncertainties due to experimental effects, uncertainties due to theoretical calculations that we need to take into account. And the way we take into account for systematic uncertainties then is by introducing Nuisance parameters, which are additional parameters for our model, which shape or model the way that our distributions after this, under the standard model condition will vary. And so we have again our test statistics formulation. Andrea showed you this before, so I'm going to go quickly on this. But what you see is that with respect to what I showed you before, we have these additional parameters, and we have this additional term, which are auxiliary likelihood terms used to constrain the value that these parameters can take. And this constraining comes from some orthogonal data sets, some data sets that have nothing to do with the data that we are interested in to inspect, and they are used just to constrain or to measure the property of the standard model so that we can constrain the value of these nuisance parameters. Once again, we have a parameterization for our alternative hypothesis in terms of the reference. And we can write it in a way that we can isolate the effect of nuisance parameters in this ratio here. So you see this ratio just describes how the distribution of the data will vary under the standard model hypothesis, under the reference hypothesis, due to the presence of nuisances. And then again, we have our neural network. So Andrea showed this before, and I'm just gonna show you the schematic view of how this looks like. We can rewrite this test statistics as the difference of two terms, and these two terms that we call tau and delta can be are computed separately and then just taken as a subtraction at the very end. One small comment that needs to be done here, or again, just to remember this, is that this term on the right side, the delta term, it only contains this, let's say, terms which are related to the reference hypothesis. So it is only able to model effects which are due to nuisance parameters, the presence of nuisance parameters in the reference. So in a way, this part of our formulation will be able only to fit those discrepancies that are present in the data, which can be accommodated by systematic uncertainties. While on the left side here, the tau term, it also contains the dependency on the alternative hypothesis HW, which now depends also on the nuisances. And this dependencies is in practical given by the presence of the neural network on the left side. So this term has an extra degree of flexibility. So we have more parameters, and those allows us to fit any source of discrepancy that can be present in the data, both discrepancies that are due to nuisance effects or systematic effects, so they can be fit by nuisances, and discrepancies that are not, and they are maybe due to presence of new physics. And so once again, the first step in the sense of implementation is again regularizing our neural network the same way we used to do before. So this didn't change. But then now we also have this additional piece, this additional term, this ratio that I showed you before in the parameterization, and we need to model it as well. And so how do we model this? Well, it really depends on the kind of systematic uncertainties we are facing. If the uncertainty is something that we know analytically, so for instance, a normalization uncertainty, which only changes the, let's say, the countings of the normalization of our histograms, then the way we write this ratio is non-analytically, and it's trivial. We can implement it by hand. We can really write it down analytically. But if the kind of uncertainties we are dealing with are shape uncertainties, so are uncertainties that change the shape of our distributions, then we don't have an analytical description for it, and we need to sort of find a way to model this part and the way and sort of approximate it. And the way we do it is by assuming that these variations with respect to the central value of the distribution, so the distribution in the default configuration, are small enough so that we can expand around this value using Taylor expansion. And so what we do is that we learn the coefficient of these Taylor expansions, and this would be a good approximation of the effect of nuisance parameters to our distribution under the reference hypothesis. So here are more details about how we do this. I think I'm going to skip this because I don't know. I don't think I have much time. So if you have any questions, we can go through this maybe later or whatever. But once we have our modeling of this ratio, and we have tuned our neural network with the regularization technique that we use with wave clipping and everything, we are sort of ready to use the algorithm. But we need to be sure that we don't that our cancellation procedure, this tau minus delta, works properly, so we don't produce any false positive in the process. Because if these two terms are not properly computed, when you take the difference, it could be that the difference is not proper, so we end up having some false positive. And the way we check for this effect is by simulating some pseudo data set where they follow the standard model distribution, but with a value of the nuisance parameters which is different from the central value. So in a way, we take some data where we know there is no signal because we simulate them, but we inject some effect due to systematics. And then we check if the cancellation works properly on those. And here is just an example of what we observe when we perform this. And it's something similar to what Andrea showed you at the really end. You see the distribution of the tau term only in green, and the distribution of t, which is tau minus delta, in blue. So when we apply some discrepancy due to systematic effects, the green distribution, so the tau only term, would shift to the right side with respect to the target chi-square. But then if delta is properly computed, when we take the difference, this shift is completely cancelled. So the distribution at the end is back to be compatible with the chi-square. And if this happens for every nuisance parameters that we have in our model, we have our nuisance parameters under control. So we are happy with our algorithm, and we can move on and look at the real data. So really extract a p-value and perform our analysis. So just a really quick overview of the 4 steps we need to perform in order to run a real analysis. Let's say, again, we first set up our neural network with the regularization technique. Then we have to find a way to model our ratio that contains the knowledge about how the nuisance parameters affect the distribution of the data under the standard model. So we have this Taylor expansion that we need to compute a priori. And once we have these 2 things, we can run our procedure. We need to validate it. And once we have done this, we can look at the data and apply the algorithm to the data. So examples, maybe it's just more interesting to see how what we can do with this. Very first application, something really simple, is a 1D problem. So at the LHC experiments, many times we search for new physics that we know the nature of, and so we can sort of select one variable which is interesting enough. So for instance, we are looking for a new particle, and we know that we want to find a resonant peak on a spectrum. This could be a one-dimensional problem. So let's say we have some bias, or we have some a priori knowledge about the nature of new physics we want to look at, we could anyway, not knowing the exact shape of this signal. So one thing we can do is applying NPLM 1D and having a test statistics, an hypothesis test that is sensitive to different shape of new physics at the same time, let's say. And here is just an example where you see there is a falling exponential falling distribution on top of which I injected narrow or broad resonance, or also just an excess in the tail. And here, so in black, you see the data, simulated data anyway. In blue, the reference hypothesis. And you see in green the distribution, the reconstruction obtained from the neural network training. So at the end of the training, if I take the log ratio of the distribution that the neural network has learned, as I showed you in the schematic at the beginning, and I just plot it on top of the data, you see it follows the actual source of discrepancy in the three cases. And this is just a simple application. But then we want to solve much harder problem, and those problems are multidimensional kind of searches where we don't really know the shape or the location of the new physics, or we don't even want to hypothesize this. And so we want to be as inclusive as possible and look at as many variables as possible at the same time, so that we are sensitive to as many scenarios as possible. And this is just an example again of a two-body finite state where we look at 5 dimensions. So these are 5 kinematic variables that are used to fully describe the kinematic of a two-body finite state at the LHC, in the assumption that the mass of the particles are negligible. So we just need the 3 momenta of the 2 particles, and then we have a symmetry around the azimuthal angle, around, let's say, in the plane, in the transit plane with respect to the axis of the beam. So in the end, we end up having just 5 variables that we can use to fully describe the problem. In this case, we also assume we have uncertainties in the reference model. So we have both normalization uncertainties and scale uncertainties. So these 2 distribution of the 2 transverse momenta of the particles can have they have an uncertainty in the scale, while all the distribution have an uncertainty in the normalization. So we encode this with our formulation with systematic uncertainties, and on top of this, I will show you that we try to look for a Z prime resonance on effective field theory kind of discrepancy. So the first thing to do again is checking whether our technique, the construction, is properly working. So again, in different configurations with different values of the systematics, we check that the distribution of the statistics after cancellation is compatible with the chi-square. And here is just an example. You see there are different scenarios for different impact of the systematics. And we managed to get, even when the tau term shifts of a lot far from the chi-square distribution, we still can recover the compatibility with the chi-square after cancellation. So we are happy with our modeling of the systematics and everything, and so we can test our technique by injecting some signals and see if we can see it. So as I said, we were looking for a Z prime signal and an effective field theory kind of signal, which comes from a form fermion content operator, dimension 6 from fermion content operator. And if we knew where to look for this kind of signals, we would have gone to the invariant mass of the two body. And there we would have seen a peak for a Z prime at the mass of the Z prime. Here is at 300 GeV. So this peak in green here. And we would have seen some excess in the tail for the effective field theory scenarios. But we don't want to add this information to our algorithm. Actually, we don't provide these variables as an input of a neural network, because if you remember here, we have just these 5 variables here, and we don't have any a priori knowledge about the invariant mass. So what we do here is just, I mean, we know in this kind of simulation, we knew we could see it in this way, but we don't give this information to the neural network. And then we just try to use our algorithm on the 5 variables that we are interested into. And here you see what the distribution would be for, again, for t and tau. So for the green distribution, again, is tau, and the blue one is t. So is the test statistics after the cancellation with the delta term. And now you see that there is a discrepancy with respect to the chi-square. So the cancellation is not complete, and the residual discrepancy that survives is the one due to the presence of new physics. So our technique sort of fit both the presence of nuisances or nuisance effects that we injected and the presence of new physics. And then when we canceled, we just canceled the effects due to nuisance parameters, due to systematic uncertainties, while the new physics is still there and we can detect it. And this is really nice. And so what we will see, I mean, once we have done this, we can play this game and say what would have been the shape of the signal in the invariant mass. So we just take our log-like Q ratio, the log ratio of the distribution that we learned from the neural network, and we project it to in the invariant mass, where we know there is a peak for the Z prime, and we know there is an excess in the tail for the effective field theory. And we see that actually here is light green here. Actually, the neural network recover the resonance, even if this was not given as an input to the neural network. And here again, you see the excess in the tail is also recovered, which is telling us that in a way the neural network learned to combine the 5 kinematic variables that we gave as an input in order to locate the signal and it rightly locate them in where the resonance is, which is meaning that it recognized the actual reason for the discrepancy. So yeah, this is just for comparison. We have similar performances with different impact of systematic uncertainties. And again, just to say, we can extract some information about a signal even if we don't give a priori information about it, which is actually useful for characterization after all. And yeah, and we can also go to something more challenging, so increase the number of dimensions. Of course, this becomes more difficult. So this is just an example where we have, again, 2 body, 2 Z particles. In this time, the mass of the 2 particles is not negligible anymore. So now the variables that are interesting are 7, because we start from the 4 momenta of the 2, and then we still have this symmetry around in the transfer plane. So we end up having 7 variables. And again, we can use these 7 variables as input, and we could inject a signal like an Higgs resonance in the invariant mass of the 2Z, but we don't give this as an input to the network. And then we will see that even if the network is not able to fully fit this, you still see that there is some discrepancy there, which is nice. I mean, it's something that motivates us to go farther and try to optimize this algorithm more. So yeah, conclusions, because I think it's super late anyway. Yeah, we have our technique, as you've seen before. We can use it for DQM, so data quality monitoring. We can use it for validating generators, and all of these things can be done without systematic uncertainties. And for those things, the technique is mature. And Marco will show you tomorrow that we also have a way to sort of do it as fast enough to be performed online. So we could do some online checking of the quality of data for online for an acquisition system, which is good. For what concerns analysis at the LHC, we have a way to deal with multivariate problems, and we have a way to take care of systematic uncertainties. So we have everything we need. And so in a way, we are ready to perform real analysis at the LHC. There are some limitations that are due to the fact that, of course, in order for the procedure to work, we need to be sure that this cancellation, when in presence systematics, works, and this depends a lot on the accuracy that we can get from our modeling of the systematics. And of course, as the higher the statistics of our data, the more accuracy is required. So in a way, the only limit that we have at the moment is on the actual luminosity that we are allowed to expand. So, but this doesn't mean that we cannot perform an analysis. And yeah, of course, the training time, I already mentioned the kernel methods technique, and we'll talk about this tomorrow. We have some ongoing work about, and we are comparing with other techniques. We are trying to understand how we can optimize the power of the method to be able to fit better any source of discrepancy in the data. So there is still ongoing work. And yeah, if you are interested into try it out for your own problem, I don't know if you have seen something that sort of could fit on your own research, but if you're interested into this, we have a Python package online with a tutorial. It's just a easy example with a one-dimensional toy problem, but it could be a good starting point. And if you have any questions about this, feel free to ask. Thanks. Yeah.
Yeah, thank you for the really nice talk. I was just curious. So obviously, at the moment, signals for new physics are pretty small. Would it not be a good test for the method to understand the uncertainties to use as your null hypothesis, like standard model without the Higgs sector or standard models without vector bosons, and confirm that you do when you use current data?
Yeah, this is exactly the idea of this last example here, where, you know, I mean, yeah, I didn't go much into the details, but the idea would be, let's say we know we have the Higgs, but we can try to remove it from the background and just use it as a signal. And yeah, it would be the first, let's say, proof of concept, I would say. Yeah.
Cool. Thank you.
You're welcome.
So there are many different, I guess, this anomaly detection techniques out there. And so have you tried to compare your thing to others?
So we are trying to compare to work from, I don't know, we can say there is a work which is similar to the one we are doing. We are trying to perform a comparison, fair comparison with them. There are many anomaly detection techniques, but they're usually different. I mean, they answer different questions than what we answer, because usually anomaly detection techniques are the purpose is to detect one anomalous event, let's say, while we are looking for collective source of anomalies. So usually techniques like autoencoders to find anomalies are sort of used to classify event per event which kind of events would be anomalous, while we don't do this. So it's difficult to
there's
compare.
Examples of, you know, there are also collective examples. For example, there have been these blind challenges like LHC Olympics and stuff like that.
Well, we haven't tried the Olympics yet. Yeah, we haven't done this. Yeah, I don't know. It's yeah. I mean, I would say.
We're referring to bump hunt, like. Yeah. The thing is that it's a fair comparison to a certain point, in the sense that the that data set to me, well, it's a collection of bumps that you can search for with bump hunting. But as Gaia is saying, we have not yet tried it because, yeah, insane. Let's say, if you just want to run the thing and see if statistically we can do that, I'm pretty sure we will be able to do well. The thing is that then that is multi-jet final state in which systematic uncertainties are probably not under control.
I know, but I mean, usually, you know, in machine learning, you try to compare to the state of the art, and you try to compare on a blind thing so that it's apples to apples. And
yeah, that's exactly what we do.
Nobody.
That's exactly what we do. We compare.
Yeah.
We compare with model-specific searches, which many people do not do. We compare with we have compared also with like, you know, these bump hunter techniques in which you know a variable in which there is a bump, and then you learn to enhance the sensitivity to that bump.
But I'm specifically asking about the blindness, right? So that you don't know what the answer is, so you cannot cheat, you cannot, you know, go back and redo it. Because this is what usually the problem is with blind analysis.
Yeah, we haven't done this yet.
Yeah, but we are fair enough not to cheat ourselves.
Sure,
Yeah.
everybody says that, but then in practice.
No, I mean, there is also one point to make here is like most of these techniques, they sort of assume that there is a bump in a given variable, and why we don't do this.
But
so in a way,
this is what I'm trying to ask. For example, in the LHC Olympics, they give you, you know, a few hundred particles, you know, for the four momenta of that. And then what? What exactly would you do? How would you go about analyzing if you have just a bunch of events? Sorry, a bunch of particles in their four momenta.
yeah, we will just apply our technique the way it is, trying to get
straight to the data, or you would try to reduce the dimensionality of the problem by you know, going to some invariant masses and stuff like that. I mean,
no, I mean, it should be like
no.
cannot be 200 dimensional, but no one can be at this stage. So
okay,
you should.
As far as we,
because in the beginning you said, oh, we just apply this to the data and that's it, right?
No, we didn't say this. I'm saying the idea here is to yeah. So I think that none of these techniques, maybe those which search for anomalies, like the autoencoders, then can deal with these 200 features, but they're looking for weird things, like point-like anomalies, like rare events. All the techniques which have to do with collecting anomaly detection, I think none of them at the moment or can never be able to deal with 200 features. So in that case of these Olympics, that we don't do because we don't think that are really so we believe that the data set should have been more varied and not made to make the bump hunt project go. So we are unhappy with that thing for reasons that are like maybe not so much scientific. But we are trying this to do the result that you want, first. And second, we believe that the reasonable approach in terms of new physics searches here would be to have final state, which are, I don't know, 2-body, 3-body, limited dimensionality. We still, there is a lot to be explored. And what we are doing, and I think also what the others do, will apply. I mean, I think we'll never work with more than 10, 20 features. We are also something, but yeah. Because it's faster to learn. Exactly. The other thing is that if you want to do data quality monitor, then you can raise in dimensionality because you have your reference, which is perfect. So you don't have to care about modeling or uncertainties or where you get the background from. So if I had to study the LHC Olympics, which is 4 jets, I know that there the quantification of the uncertainties is probably going to be, well, either very difficult. I'm not able to do this because I'm not an experimentalist, and I think I will fail. So I think that should be addressed. Yeah. That's why I think that is not a particularly useful exercise, because I don't think no. But okay, we will try technically.
You know, it's 4 jets now. Once they reveal it, you know, a priori it was just a bunch of particles and that was it, right? So anyway, I'm just trying to say there's a value in doing it completely blindly without knowing what the answer is.
I think someone else should provide a number of there should be some wise person providing a really blind data set, unbiased and like aiming to physics and not to something else. Sorry for taking too long. Maybe the talk should be shorter, but happy that there were quite some questions. So thank you.